Alright guys, what time is it? Afternoon, or whatever time you were watching this. This is Mr. Breslin. I am sick, so I'm going to be weird sounding, and this is stuff you missed because you value youth and government over AP Chem. Okay, so we were talking about titrations, and we had done strong acid, strong base, we had done weak acid, strong base, and so we have to do a couple of these. So there'll be some problems on here, so if you want to actually work out the problem yourself, then hit pause at some point, and then yeah, otherwise we're just going to go through it. I've already worked it out. I'm just going to be highlighting some stuff. So here, first one, if I titrate 50 mils of 0.100 molar HCN with Ka value of 6.2 times 10 to the negative 10th with 0.100 molar NaOH, what's the pH at the equivalence point? So if you want to actually do it, hit pause. If not, here it is. So to first find out, we have to first find out what volume of NaOH we used. So we're going to use the molarity of acid times the volume of acid equals molarity of base times volume of base. And we have the molarity of the acid from up here and the volume of acid and the molarity of the base. And obviously because they are the same concentration, they're going to be the same volume as well. So you had volume of base at 50. That'll become important later on because you have a total of 100 mils, a total of 100 mil solution. So we look at what is in solution at the equivalence point. And at the equivalence point, we had 50 mils of acid and 50 mils of base, and we had equal concentrations of each. So at the equivalence point, you have water and you have sodium cyanate. So the sodium ion, this is soluble, so it breaks apart. The sodium ion does nothing, it's just sitting around. It's the cyanate ion that actually does anything. So now, because it was 0.100 before, and now there is 100 mils of stuff, now it has dropped by half, and so now it is only a 0.050 molar cyanate ion. Now that is a weak base. Why is it a weak base? Because it was the conjugate base of a weak acid. HCN is a weak acid, which means that its conjugate base is going to absorb hydrogen ions to some degree. Where's it going to get the hydrogen ions? It's going to get them from the water. So we have the CN minus, and it is 0.050 molar. And the water we don't count because it's a liquid, and there's 0 and 0 of that. And then we work it out the same way we do all ice boxes. Now, it gives us the Ka value here at the beginning, but we don't want the Ka value, we want the Kb value, because this is the base. This is acting like a base right now. So, to get Kb value from Ka value, we use this equation, Ka times Kb equals Kw. So, Kw is always 10 to the negative 14th, and the Ka was 6.2 times 10 to the negative 10th. So, we put those two over each other, and we solve for Kb, which is 1.612 times 10 to the negative 5th. So we put that over here, and we put our equilibrium concentrations of our stuff, and we get x squared over 0.050 minus x, which was this, and we super hope that the x is negligible when subtracted from 0.050. So when you solve for x, you get 8.98 times 10 to the negative 4, and that is the OH minus concentration. That is this, the OH minus concentration. Sorry, I'm going to cough from time to time, because, yeah, I am. And so the pOH, based on the OH concentration, is 3.047. And so when we add 14 to that, because the pH plus the pOH equals 14 always, then the pH is 11.0. And it's a good idea to keep at least 1 decimal point for the pH when you are actually answering this on the AP test. They usually won't count sig figs when you're doing a pH thing, because sig figs when you do a logarithm are weird. So, okay. So that is how to do that problem. That's what I gave as a warm-up on Thursday. All right, the next problem is a little bit harder. The next problem is a little bit harder, and that's this problem, because the volumes are not the same, so the concentrations are not going to be the same, so yeah. So the next problem, I titrate 80 mils of formic acid, which is HCO2H, with a Ka value of 1.77 times 10 to the negative 4, with 0.085085 molar NaOH. I find that it takes 58.6 milliliters to reach the equivalence point. And there's a difference between the equivalence point and the end point, which I'll talk about a little bit later when we talk about indicators, but don't worry about it for now. All right. Well, first of all, what is the concentration of formic acid, which is what you're usually trying to do when you try to figure out when you're trying to do a titration. And then second of all, what is the pH of the solution at the equivalence point? So we first have to figure out the concentration of the formic acid using the same equation that we were using before. Molarity of acid times volume of acid equals molarity times volume of base. So we know everything here except for the molarity of the acid. So we put in 80 from the problem, and we put in the molarity and the volume that we had from the base, and we solve for the molarity of the acid, which was 0.0623 molar. So that is just A, what is the concentration of the formic acid? Should probably say what was the concentration of the beginning of the formic acid, but you understand. All right, though for B, this is the reaction that's going on. So we have HCO2H plus NaOH reacts to form H2O plus NaCO2H. And the water doesn't do anything. The sodium ions don't do anything. The only thing that does anything is the CO2H ion. And again, because it is the conjugate base of the weak acid, it itself is a moderately strong base. It's a weak base as well. So it's going to do something. So we had at the beginning 0.623 molar acid, and there was 80 mils of that, and there was 58.6 mils of the NaOH. Doesn't really matter what the concentration was. So at equilibrium, here was the original concentration of CO2H, and here is the diluted concentration. So we had 80 mils of it at the beginning, and we had total 138.6. We added these two together, so we have total 138.6 mils. So when you multiply by this ratio, we get the diluted one. Really, we're using the equation M of the, can you even see that? Yeah, M1 times V1 equals M2 times V2, where we have the molarity times the volume of the concentrate, which was this, equals molarity times the volume of the dilute. And so the volume, this 138.6, is really this volume, so we divide both sides by that volume, so we get M1 times V1 over V2 equals M2. So that's really what we've done here, and that equals the molarity of the dilute. So that is the concentration we put into this equation. Again, it is the base. It's acting like a base. It's absorbing hydrogen from water. And so that is the concentration we start with. We have none of those. And so we do minus x and plus x and plus x. And then we find Kb again, just like we did last time. Here's the Ka from the problem up here. It gave you the Ka. So here's the Ka. And we know Ka times Kb is Kw. So Kb is Kw divided by the Ka. And Kw is always the same. It gives you that on the equation sheet on the, equation sheet on the AP test. Will give you that on there, and this equation as well. And so we find Kb is 5.65 times 10 to the negative 11th. And we put that over here, and we substitute our x times x, which is x squared, and we put that on the bottom because it's always products over reactants. We get x equals 1.425 times 10 to the negative 6, and that is equal to the OH minus concentration. So the POH is 5.846, and if we add 14, or we subtract that from 14, we get 8.154, and again, it's a good idea to keep at least 2 sig figs, keep one decimal point, one place past the decimal point on pHs, so I'd round it to 8.2. Yeah, there's a complex way to do sig figs with logarithms, but I don't want to talk about it right now, so there it is. All right, there is that one. If you didn't understand, I'll go over again right now. Just put rewind. Okay, so anyway, rewind, yeah, because it's like a VCR. Yeah, just click, slide the bar back, slide the bar back. It's like down here, slide something, I don't know. All right, so anyway, so we talked about already strong acid, strong base. Excuse me. Coffee. Coffee. All right, so we talked about strong acid, strong base. We talked about weak acid, strong base. We have not yet talked about weak base and strong acid. Now, somebody in class, I forget who, asked about weak base, weak acid, and they won't give you one like that. So I have never seen one. I can imagine what would happen, but it doesn't matter. It would be, yeah, it would be weird because you'd have both conjugate bases in there at the same time, and so then the pH of the equivalents would have to be, yeah, it would be too complex to do, so whatever. Okay, so let's say that we have a weak base with a strong acid. We have 100 mils of 0.050 molar NH3, that's a weak base, with a strong acid, 0.10 molar HCl. And the Kb this time of this thing is 1.77 times 10 to the negative 5. So because it is a weak base, it's going to start with a high pH. It's going to start with a pH up here somewhere in the 11 to 13 range, depending on how much of the base and how concentrated. So the pH, as you titrate, is going to go down, and it's going to have its equivalence point just the same way. It's just going to go down. And here's the reaction that's going to go on. Now, I didn't give you the volume of acid that you would need. You would actually need 50 mils because it's twice as concentrated as this, and so you need half the volume, and we're using the same molarity of acid times the volume of the acid equals molarity of the base times the volume of the base, and yeah, you put those in there, and you can solve for volume, and it's 50 mils. All right, that becomes important because we're going to need it for the dilution over here. So the the reaction that's going on is the NH3 plus the HCl. So the NH3 is a base, so it absorbs the hydrogen ion from HCl and forms NH4 plus Cl minus. Now you could put this together in an ionic compound, but really it's soluble, very soluble, because NH4 is very soluble. So it's going to break apart. And it's the NH4 that is going to do anything. Cl minus is the anion of a strong acid, so it is an extraordinarily weak base. This is not going to absorb like the other weak bases did, like the other conjugate bases did in the weak acid strong base one. The conjugate base of a weak acid is a moderately strong base, but the conjugate base of a very strong acid like HCl is an extraordinarily weak base. It's still a base because everything's a base, everything can absorb hydrogens, but it's so incredibly weak that it doesn't matter. Okay, so we had 100 mils of this, and we had 50 mils of that, which means that our total volume, when we're figuring out what concentration of this we have, our total volume is 150. So we're using kind of the same equation as we had before. So we originally had 0.05 molar NH3, and then we had 100 mils of that, and we had 150 mils total. So our concentration of NH4 at equilibrium, at the equivalence point, is going to be 0.033 molar. That's going to be the concentration of NH4 plus. So that's what's going to go into our equation over here. So what's going to change the pH from 7 at this equivalence point is going to be the NH4, because part of the hydrogens are going to break off because it's a moderately strong, or not moderately strong, it's just weakish acid. So we got the beginning concentration, we got minus X and plus X and plus X. And again, now they gave you the KB because they always give you the thing you don't need, so you can calculate the thing you need using this equation. So they give you a point for using the equation. So they gave you the KB, so the KB was 1.77 times the negative 5, so now we just solve for Ka the same way. Kw is always 1.0 times 10 to the negative 14, divided by 1.77 times 10 to the negative 5, and we get 5.65 times 10 to the negative 10. So it's a very weak acid, a very small number up here, very weak acid. So we put that number over here, and we put x squared on top, and 0.33 minus x on the bottom, and we super hope that is negligible, which everything pretty much is, always. And because it's a waste of time to actually do the quadratic on the AP test and stuff. So, all right, so that works out. X is equal to 4.3 times 10 to the negative 6, and we don't have to find the pOH and find the pH the roundabout way because this is the concentration of H+. So this is already the concentration of H+, which means we can just take the negative log of that to find the pH. And so the pH is 5.4. Okay, so that was a weak base and a strong acid. So next that I want to talk about is a kind of interesting concept called, or an interesting thing you can do with titration called the half titration. Now, what the half titration means is it's a thing you can do if you have a pH curve, if you have the curve of, and let's say that we're doing weak acid strong base, because that's by far the most common thing that we'd be doing. So if you have a weak acid strong base, the pH at the equivalence point would be up here around 9, or whatever it happened to be, 9 to 10. Up here. And we could work that out if we knew the concentrations, but that's not what we're doing right now. So let's say that it took 50 mils, that the equivalence point was at 50 milliliters. So at 50 milliliters, this reaction has gone forward entirely. So we're basically saying the concentrations of these two things are 0, and the concentrations of these things are really, really big. Really, the concentration of F minus or the of HF is not 0, because you can still use this equation, because it's still got the stuff in there, to figure out what the concentrations are. But if we look not all the way at the equivalence point, but we look back here at halfway to the equivalence point. And by halfway to, I don't mean halfway to in pH. So I don't mean if this was a pH of like 10, I don't mean pH 5 automatically. I mean halfway in the volume. So half of the acid has been neutralized. So right here at 25.0 mils. And this only works if you know the graph, because otherwise you don't know what the volume was and you don't know what the pH was at that volume. So let's say we have right here at 25 mils, we have a pH of like 3.14. So let's just say that's what it was. And they would have to give it to you on there. They probably wouldn't ask you to read it off the graph. So they'd have to give it to you on there, and they'd probably give you some other points as well just to throw you off from stuff, and they'd give you a whole bunch of the data. And the one that's halfway is the one you really want. Because at halfway, that means that the molarity of the HF is now equal to the molarity of the F minus, because half of this has reacted. Whatever the concentration was at the beginning, it doesn't matter what the concentration was, since half of it's reacted and turned into F minus, we have the same concentration of HF as we do F minus. And if we have the same concentration of HF as we do F minus, and we put it in the Henderson-Hasselbalch equation, that means that these two are the same. So let's say that both of them were 0.033 molar. 0.033 molar at the halfway point. That means that both of these are 0.033 molar, which means that this term is 1, and the log of 1 is 0, so we can get rid of this term, which means that at the halfway point, the pH is equal to the pKa. And if you know the pH, you can know the pKa. So if you have the pH is equal to 3.14, then the pKa is also equal to 3.14. And if you know the pKa, you can take the Ka is equal to 10 to the negative 3.14. And you know from this the Ka is 7.2 times 10 to the negative 4. And that happens to work out that HF has a Ka of 7.2 times 10 to the negative 4. So you can actually determine the Ka value for a weak acid from a titration if you are doing the curve. If you're actually doing a titration curve, then you can find the Ka value for a weak acid. You can use that to identify the acid, or you can, whatever. They ask you to find the Ka value. All right, so that is just kind of a way you can use titration in another way that not everybody knows, and now you do. Okay, just a note before we go on to no, actually, let's go on, and then we'll come back to that. Okay, so the other thing I want to talk about is indicators. So an indicator is anything that changes color based on the pH of a solution. An indicator is always an acid or a base. Well, it is both. It's a weak acid that has some kind of Ka value. So the indicators that we know, phenolphthalein, and like bromothiamyl blue, and methyl red. There are dozens and dozens of indicators, and they all have different ranges at which they change, and that's why we need a bunch of indicators, because some titrations change at pHs. Their equivalence points are somewhere in the 9 to 10 range. If it's a strong acid, strong base, it's going to be somewhere in the right around 7, with 6 to 8 range, and if it's a weak base and strong acid, the pH at the equivalence point will be somewhere in the 5 to 7 range, even 4 to 6 range. So we need different indicators because they change colors at different pHs. Now, on the AP test, they might give you a list of these. They might say, okay, here's a titration curve, and it looks like this, and the pH at the equivalence point, and you find that the pH at the equivalence point is like 9.6 or something like that. And they say, okay, which of the following indicators is best for this titration, and explain your answer, or justify your answer. So they might give you a list of these, and they might give you the Ka values for each of these, or they might give you the pKa values, or if you're lucky, they will give you the actual pH ranges. So for phenolphthalein, the range of the pH is somewhere between like 8 and 10. For bromothiamyl blue, the pH is somewhere between 6 and 8, and for methyl red, it's about 4 to 6. So for this one, if they actually give you the pH range, then it's easy because 9 to 6, it must be in this range. So phenolphthalein, because phenolphthalein, it has the right pH range. They don't always give you the pH range. Sometimes they give you the pKa. Now, the pKa for phenolphthalein is right in the middle of its range. So the pKa for phenolphthalein is about 9, right? So you can know what the range is from the pKa because the range is about plus or minus 1 from the pKa. So the pKa plus or minus 1 pretty much equals the pH range. So the pH range for an indicator is the pKa plus or minus 1. So 9 and 8 to 10. And then this one, the pKa would be about 7, and this one, the pKa would be 5. Now, they may not give you the pKa, although that is the most common thing they'll give you. They might give you the actual Ka value, and you'd have to take the negative log of it. So this would be just 1 times 10 to the negative 9, and this would be 1 times 10 to the negative 7, and this would be 1 times 10 to the negative 5. So that is another possibility of what they could give you. They could give you those. Now, usually you're not doing what's called a potentiometric titration. A potentiometric titration is one where you actually have a pH meter in the reaction vessel itself, and you're monitoring the pH, and you're watching it go up, and you're creating the graph, or you're having some logger software actually create the graph for you. That's called a potentiometric titration. Normal titration, or an indicator titration, is where you actually have an indicator inside there. You figure out kind of what it should be, if it's a weak acid, strong base, or whatever, and then you look for a color change. Now, if you're doing an indicator, you're going to reach what's called the end point. The end point is right where that indicator starts to change color. So the end point is determined by an indicator color change. Now, we've been talking about not about the endpoint, but the equivalence point. The equivalence point, that is when you actually know the pH and know the scale on there. You can see the actual curve. Now, if you can see the curve and see the inflection, that is the equivalence point. Or if you know the moles of the acid and the moles of base, then you can know what the equivalence point is. So the equivalence point is determined by the graph or by stoichiometry. So determined by the graph or by stoichiometry. Okay, so that is basically, I think, everything that we had on there. There was a worksheet that the people who were here got on Friday that they had some time to work on, but I think I'm going to put that in a different video. So we're done for now.